Okay, let's walk through this problem about a quantum system in a time-dependent field. So we are looking at the problem description. We have a quantum system and it's described by this Hamiltonian HH is equal to minus j sigma z plus lambda of t sigma x. Here sigma I, where I can be x, y or z, are the well-known Pauli matrices. J and lambda are positive constants and importantly j is much greater than lambda. Now the time dependence comes from lambda of t. It's a piecewise function. For time less than 0, lambda of t is 0. For time between 0 and t, it's equal to the constant value lambda. And for time greater than t, it goes back to 0. We are told that at time less than 0, the system is in its ground state. And what we want to find is the probability of finding the system in the excited state at a time much greater than t. We need to find this probability in the leading order in lambda. And we have a few options here for the answer. Let's lay out our solution approach. First, we recognize that the Hamiltonian is time dependent. Its h equals minus j sigma z plus lambda of t sigma x. We know the system starts in the ground state at time less than 0. And our goal is to find the probability of transitioning to the excited state at a time much later than t. The condition that j is much greater than lambda is a big hint. It suggests that the time-dependent part, the term with lambda, can be treated as a small perturbation. So we should use time-dependent perturbation theory. Let's start with step 1, analyzing the unperturbed system. For times less than 0 and greater than t, lambda of t is 0. So the time-dependent term vanishes. The Hamiltonian in these periods is just the unperturbed Hamiltonian H0, which is minus j sigma z. We know the sigma z matrix. It's a 2 by 2 matrix, 1 0 in the first row and 0 minus 1 in the second row. So H0 is minus j times that matrix, which gives us the matrix minus j0 in the first row and 0j in the second row. Now let's find the eigenvalues and eigenstates of this unperturbed Hamiltonian H0. The energy eigenvalues are the diagonal elements of this matrix. The ground state energy Eg is minus j. The excited state energy EEE is j. The corresponding eigenvector for the ground state associated with energy minus j is the column vector 1 0. We'll call this vector ket g. And the eigenvector for the excited state associated with energy j is the column vector 0 1. We'll call this ket e. Step 2 is identifying the initial state. We were told that at time less than 0, the system is in its ground state. So our initial state vector at time less than 0 is ket psi at time less than 0, which is equal to ket g, the column vector 1 0. Now for step 3, applying time-dependent perturbation theory. The perturbation is the time-dependent part of the Hamiltonian v of t, which is lambda of t sigma x. For the time interval where the perturbation is active from 0 to tv is equal to lambda times sigma x. The sigma x matrix is 0 1 in the first row and 1 0 in the second row. So v is lambda times that matrix. We want the transition probability from our initial state ket g to the final state ket e over this time interval from 0 to t. The formula for the first order transition amplitude, which we'll call CE super 1 at time t, is given by minus I over h bar times the integral from 0 to t of the matrix element bra e v of t prime ket g times e to the power of I omega egd prime dt prime. The energy difference between the excited state and the ground state is bar omega eg. That's ee minus eg, which is j minus j, so it's 2j. The transition frequency omega eg is therefore 2j over bar. Continuing with step 3, let's calculate the matrix element. We need to calculate bra e v ket g. This is the row vector 0 1 times the matrix lambda times 0 1 1 0 times the column vector 1 0. We can factor out lambda. So it's lambda times the row vector 0 1 times the matrix multiplication result of 0 1 1 0 with the column vector 1 0. Doing the matrix multiplication 0 times 1 plus 1 times 0 is 0 for the first row and 1 times 1 plus 0 times 0 is 1 for the second row. So we get the column vector 0 1. Now we multiply the row vector 0 1 by the column vector 0 1. 0 times 0 plus 1 times 1 is 1. So the matrix element bra e v ket g is equal to lambda. This value is constant for the time interval from 0 to t. Still on step 3, we evaluate the integral. We substitute our matrix element and the transition frequency into the formula for CE super 1 at t. Since lambda is constant, we pull it out. We then evaluate the resulting exponential integral from 0 to t. After evaluating and simplifying the prefactor, we apply the limits of integration. Simplifying e to the power of 0 and rearranging the terms, we get the final expression for CE super 1 at t. Now for step 4, calculate the probability. The probability of transitioning from the ground state g to the excited state e is the square of the magnitude of the transition amplitude. Pg to E equals the magnitude of CE super 1 at t squared. We need to calculate the magnitude squared of the term 1 minus e to the power of I theta, where theta is 2jt over a bar. There's a very useful identity for this. The magnitude squared of 1 minus e to the power of I theta is equal to 4 times sine squared of theta over 2. In our case, theta is 2jt over a bar. Continuing with step 4, to get the final probability, we substitute theta equals 2jt over h bar into the probability expression. Pg to e is the magnitude squared of lambda over 2j times 1 minus e to the power of I 2jt over h bar. This is the magnitude squared of lambda over 2j times the magnitude squared of 1 minus e to the power of I 2jt over h bar. The magnitude squared of lambda over 2j is lambda squared over 2j squared, which is lambda squared over 4j squared. Using the identity for the second part with theta equals 2jt over its magnitude squared is 4 times sine squared of 1 half times 2jt over h bar. So Pg to e is lambda squared over h bar base squared times 4 times sine squared of jt over h bar. The 4 in the numerator cancels with the 4 in the denominator. This leaves us with the probability Pg to e equals lambda squared over j squared times sine squared of jt over h bar. Finally, let's look at our result and match the option. Our calculated probability is lambda squared over j squared times sine squared of jt over h bar. Let's compare this with the given options. Our result, lambda squared over j squared sine squared jt over h bar, exactly matches option number 2. So the final answer is lambda squared over j squared sine squared jt over h bar.